The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it. A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space. If we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line. We can check this by resuperposing the path line you saw earlier. Often it is useful to use multiple streak lines to observe a flow field. We can make them with the multiple finger wire you saw before. The third concept we need is the timeline. A timeline is defined as the instantaneous location of a line of fluid particles marked earlier at a prescribed location in the flow. These lines are usually most useful if the marking location is normal to the flow direction, since then the location of the timeline, a short time later, shows the velocity profile of the flow field. Here we apply the timeline technique to a steady flow past an airfoil. Near the angle which gives zero lift, the portion of the timeline passing above the airfoil rejoins the portion passing beneath at the trailing edge, except for the narrow boundary layer region where the flow is retarded by friction. Since the distance around either side of the airfoil is approximately the same, the timelines show that the average speed above the airfoil is approximately the same as beneath it. When the airfoil is set at angles which give large lift, the portion of the timeline passing above the airfoil outruns the portion beneath. The velocity is higher near the upper surface. At negative incidence, the effects are reversed. The fourth concept we need is the streamline. A streamline is defined as any line that at a given instant is everywhere tangent to the velocity vectors of the flow field. The streamline is essentially a mathematical idea and is very useful in many fluid flow analyses, but there's no way to make a streamline directly visible. You've seen that in steady flow, the path line and the streak line are the same, and you might suspect that the streamlines would coincide with them also. This is in fact the case. Consider a particle moving along in steady flow. As you saw, each particle moves down the same path line, so that it's always moving down this path towards the particle ahead of it. This means it is always tangent to the path, and that is how we defined a streamline. So in steady flow, the streamline, the streak line, and the path line are all the same, and we can use either streak lines or path lines to show us the streamline pattern. Another thing we often need is the velocity vector field itself. We can find the velocity field by using what I call combined time streak markers. The bubble squares you see here are such markers, and they have a number of useful properties that you can prove for yourself. The sides of the markers are streak lines. In steady flow, the sides show the streamline pattern. The fronts and backs of the markers are timelines. In a two-dimensional incompressible flow, the area of each marker is forever constant. Since the time interval for a given marker to pass any fixed point in space is also constant, the length from the front to the back of a marker at any location is a measure of average velocity in that region. Also, the distance between the sides of a marker is inversely proportional to velocity. Now consider for a moment an unsteady flow, like the one you see here past an oscillating plate. Do you think that in this case the streak line or the path line will be the same as the streamlines? Let's look at a path line and see. Here is a single marked element entering at a fixed time in the cycle of a plate. As before, we superpose its path line. Now compare the path line with a succession of instantaneous streak lines entering through the same point. None of the instantaneous streak lines coincides with the path line. Here is a second element entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate. Now you see elements marked at both times in the cycle of the plate. If we superpose the path line of the second element and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either. Now let's see about the streamlines. In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here. If we take a transparency of one frame of the multiple time streak lines and overlay on it another transparency taken a few moments later, we can connect the endpoints of the streak lines and show the particle paths for short time intervals. Here you see the short dashes made by connecting the endpoints of the time streak lines. They show us the velocity direction at each point. If we draw lines parallel to them, these are the streamlines. The total streamline picture you see here is for the same instant that the first particle we observed with a path line entered the frame. The dotted streamline is the one that passes through the same point. If we compare the dotted streamline with the path line through the same point and at the same instant in time, you see they are quite different. If we compare the dotted streamline with a set of streak lines entering through the same point, they do not coincide either. In a transient flow, the streak line, the path line, and the streamline are all different. If the streak lines move sidewise, as you see here, then the flow is transient, and we cannot use the streak lines for streamlines. In a transient flow, we must work out the velocity field from some kind of combined time streak markers. We've seen one way to make the flow visible. Now let's see how to use this information to solve engineering problems and as a basis for mathematical analysis.